It's got to be intensive. So I'm explaining everything. Try to explain everything. So missing some of the contents like chapter 1 and 2. But I will start from bondings again. Okay, the different type of bondings, and then move on to intramolecular forces. Vesper theory, if you're not too sure about that one. If I have a time, I might talk about a bit about atomic models, the Bohr's and the Schrodinger's model too. But I try my best to explain the Schrodinger's model in the module test explanation. So it's got to be a busy day for me too, because I need to explain every module one content. But I think we need it. We definitely need it, because I have like more than half of students, they don't really know what's going on. And I don't want that to happen. Okay, now I'm on live, okay. I give you a print of today's work. Boo.
I went to the libraries in Korea to study, and
did ya?
Because like at home it's hard because like
you would never.
The libraries are nice. They have like cafeteria and everything.
It's not a library. Like, don't they call it like a study cafe or something? Yeah. I've been once when I went to Korea last year. Then I'm like, whoa. And they're quite. Did you pay for that?
No.
The free? Oh, that's good.
Might have to redo a lot of the bonding part of the.
Yeah, you better do finish that, the bondings.
The bonding part of the thing.
Yeah, the one we're doing.
Because I got like confused with like what to draw and stuff.
Yep. Okay, give you a supplementary notes for today's class, so you can have a look at that too. So we're gonna start in 5 minutes. Oh, I don't know where that. morning, Yara. School starts tomorrow.
Yeah.
Hello, Matthew. Private school started yesterday. Yeah. Well, why came back to school? Hello, Matthew. Okay. Just waiting. Print. School starts again, and well, fresh starts, year 11. Okay, so do you guys get any like senior ties or senior like something ties for gents, boys, and ladies? No, nothing. Oh, blazers or any new chests? No, you're done. You guys get the you guys get jersey quite early. Yeah, and term 3, term 4. So that's exciting. I realised that they're wearing jersey this hot summer day too. I'm like, oof. Why not? Just 1 year you can wear. Just checking. I'm on live. I am live. Okay, I'm on live now. All right. Let's start. Just quickly revising what we learned up to now. Just okay. I will try to revise it again and again and again. So, all right. When the school starts, you'll start from obviously module 1, and so revising all the motions like velocity and vectors too. You'll learn more about those the vector diagrams, and most likely you will finish module 1 within 2 to 3 weeks in schools. So they finish really quickly on rushing it because we assume that you learned that in school, year 10, so kind of pretty awesome knowledge, and move on to the module 2 as well too, and they're gonna move really quickly because Newton's law is actually pretty awesome knowledge. That's what we learned in the year 10 as well too, but not much in depth most likely. So this is why I'm spending quite a lot of time giving some ideas about what the Newton's law is. So last 2 weeks, we started module 2, we started learning about this, the force, okay? Matthew, sorry, you again, okay? How would you define force?
Like an interaction between like objects that changes in motion.
Changes in motion. So whenever we're saying that we heard about the force, it's key word to understand force is a change in motion. Change in motion. So this is a key word to describe explaining everything, Newton's first, second, and third law. That when there is a force, there will be a change in motion. Just try to understand as, okay, that's a change in motion. But it's important to understand what the change in motion is. Then, Damien, can you describe what would be the meaning of the change in motion then? Just generally. It's not like a scientific or like a physics. When I say, hey, what can you describe me? What do you mean by change in motion?
Moving faster.
It's got to be. Could be something like moving faster. Anything else?
Slower.
Maybe slower. Anything? In terms of movement, how do you describe? Oh, you have a change in motion.
Stopping.
Stopped. You actually stop or change, slow down. What about changing? Like I change the direction. I can't say that's the same motion because initially I was moving forward and now moving backward. That's a change in motions too. So please use those everyday example, or you think about the imagination about, okay, change in motion means like getting faster, getting slower, getting stopped, or like change in direction. But if you realize that I'm basically talking about, this is all about acceleration then. Why? I've been emphasizing this, and acceleration is all about change in the velocity. Does it make sense? Okay. Now, change in velocity can have the 3. Again, let's revise that. You can either have change in the magnitude, that means that you're getting faster, you're getting slower, or change in the direction. And you can also have change in both. Change in both of the magnitude and direction. Means that in any of those situations that we have change in the velocity, we are able to say, oh, there is a change in, or there is an acceleration. Therefore, there is the force applied on you too. Okay, but let me think about this situation here. I have two boxes, say 10 kilo and the 5 kilo. Okay, you're pushing that 10 kilo and 5 kilo over here with the same amount of the push. So what I mean is you push that with the same amount of force. Okay, all right. If I push the 10 kilo and 5 kilo with the same amount of the force, so I'm trying to push them the same amount, okay? Will these two have any differences in terms of their motion?
The 5 kilo one will
Move more, or move more faster, or move forward. So you will experiencing the greater change in the motion than 10 kilo, simply because they're heavier. Okay? Now, the way we can describe that in mathematically or like in physics is where we use the F equals to ma from it then. Okay? When we apply the same amount of force on both of 10 and 5 kilo, because we have a mass difference of that, then we'll have the change in the acceleration differently. Does it make sense? Okay? So as I describe that, it will it will appear as it will move the shorter distance or the longer distance, or it will move faster, slower. That's what you need to imagine a lot until you finish your HSC. Okay, we're gonna come back to these forces again. You're gonna reuse the force, but I don't think I have a time to explain what the force is at the time. So make sure you understand what the force now, or like by February. Okay, you have a month of time to understand or try to get some essence of the forces too. Just try it, push it, challenge it until you finally understand, oh, force is not just the F equals to ma, it's about change in motion. So think about what happens to when you get a change of the forces too. And then we'll also learn about vector sum. Obviously, the head to tail, producing the A and B, producing A plus B. We've been doing this quite a lot. And I've been asking you, yeah, you think about what I mean by that too, in terms of the forces. And we learned about the net force. Okay, net force simply means that the sum of the forces, so all the force 1 plus force 2, all the force components that you have, and therefore we can able to do that. But this is all the vectors too, means that we are able to produce the force 1, force 2 goes like this, and making the force 1 plus 2 go like that. Hello Andy, okay? Okay, make it things like this as well too, okay? So I'm dealing the net force as the same as the vector sum, that we're adding up the forces from head to tail and tail to head, okay? In this case, you may need to use the Pythagoras, trigonometry, sine rules, cosine rules too. I don't know, you may get everything. Okay, you sometimes get really complicated mathematical questions, so I know you kind of get like overwhelmed, like, oh, why so many like equations and so many numbers there in the physics, but you know, sorry that. I must tell Newton's the one that gets some mathematicians too, so he loved to put everything in the mathematically too. It's kind of language. Okay, that's what about net force, and we learned about this static equilibrium. So remember that static means something like stays in the equilibrium state. So it means that we have a two situation having the static equilibrium. It's either be you're in stationary or you're moving in the constant velocity. But both of the situations telling you something. Matthew, stationary, or the two situations that we have a stationary position to or moving in the constant velocity there, okay? What does it represent? What does it represent? Let's talk about in terms of motion, okay? In terms of motion or movement, what these two are representing. I come back to you, John.
They have no change in motion.
No change in motion. No change in motion then. No change in motion. Very good. Then, what you need to think about from here is, let's bring this one back. we define that force is change in motion. So when there's a change in motion, we decide to say there's a force. Yeah? But there is no change in motion. Can we reinterpret that as then there is the net force is 0? Okay, or can we reinterpret that as, oh, that net acceleration is a 0 too? So this is what I mean by, again, please read the question very carefully. The questions provide you the situation that whether that is static, like the equilibrium or not, they're like the stationary, moving constant velocity. That is kind of hidden information, but it's also at the same time given to you. Okay, they are already probably like presumed to know that, oh, you know about like a net force is 0 in the stationary or moving the constant velocity. Okay, so last week we started learning about the slightly different situations. Then I asked you to analyze some of the forces in this, the force diagram. For the force diagrams, I've been asking you to draw that all the analyze all the force components there. So for example, if we push that with a certain force, okay, we call it dragging force, a pushing force there. There will be in the horizontally, we have the frictional force, which is found by mu r. Where the mu stands for the coefficient, the friction coefficient. So that means simply depends on what type of surface you have. You may have the different coefficient values. Like a concrete would have the greater coefficient value because it's the rough, creating the more friction. Icy road would have the lower friction values because of characteristics. Okay, and we also learned that there is the weight force that's found by mg. Okay, and most importantly, we have the R. That's known as what? Normal. The reaction force. Now, that normal means that, not like I'm describing normal like a normality or something. It means that perpendicular always. Perpendicular. The easiest way to think about normal is that we have, if you learn the mathematics, you have a tangent. The normal of the tangent means the perpendicular line of the tangent. Okay. So normally it's a mathematical term that we're using in physics too. That means perpendicular reaction force, but perpendicular to the surface. So last week we started learning about this. When something is going uphill and downhills from it. Okay. Do you remember that we have a forces applied in here too? So that we have a weight force, which is pushing it down. Okay. We have dragging force, like this situation on the up, and we have a friction force that's pushing it down, okay? And then there will be a normal reaction force, which is going upward like this here. Now, whenever you have a diagonal vectors, remember that the diagonal vector means that we have the horizontal and, so there's a V, we have the horizontal and the vertical components in the right angle triangle like this, okay? For this type of uphill and downhills, instead of dealing with the 3 diagonal vectors, I've been asking you to draw that, a diagonal vector, take that weight as your diagonal vector, so take this as horizontal and vertical components there. So it means if this is a theta, that would be theta angles too. The easiest way to think about this, so assume that you're in the uphill downhills, it's moving along with the surface like this. So the angle made by the weight force to the normal is, or the plane, would be exactly the same as another angle of the incline and decline. And that would be weight force, so mg of the y, and that would be mg of the x. And this is the way we can deal with some incline and decline. Okay, so the force diagram here. But last week we started learning about the situation that is not in the stationary, that will not in the moving the constant velocity. So that was giving you that the net force may, in this case, may not be 0. Yes, there was a situation that it was, if the box is stationary here, that means we can apply the static equilibrium. But what if this is not stationary? And the question we're asking you that you need to find it out, what if we have the situation that this box is sliding down? Okay, then find it out, the forces too. And simply, I've been asking you to find that, all that, net force on X, net force on Y, adding that all together to combine them all together, and then you're able to find the net force value. Okay, this is something where we're up to. Okay, of course, we learned about pulley. No one likes pulley, I know that, okay? Pulley is simply the tool that changes the direction of the forces. So you remember the tension force we talked about? if a mass is hanging over there too, it creates the weight force is pushing it down, mg. Okay, and it creates the tension force. Think about the way we're hanging something. It will create tension force on the top. Okay, in this perspective, this is the tension force from the on the perspective of the mass m. But there will be another tension force that is created from the wall side there too. So there will be equal amount of tension force generated from the top. So the tension force is kind of special type of force because it has the both of the action and the reaction forces applied to it. So we're going to talk about more details about action and reaction force. But remember that tension force would have the two forces in the equal amount with the opposite directions. But it depends on the way you look at. If you look at from the perspective of the mass hanging, you will have the weight force pulling it down and tension force kind of pulling it up. So that therefore it will reach to the static equilibrium. In the perspective of the wall there too, there will be a tension. There will be like some wall hanging force on the top, and the tension force pulling it down. Remember that when you put hanging something, there will be a tension force generated on the point hanging to the wall there too. Okay, so there will be another tension force applied there too. Does it make sense? Okay. This is something that you is useful to think about in here. But what if we have two? You got to talk about this later. What if I'm hanging the two masses? Okay, say big mass M and M here like this. Then you may need to think about there will be a tension force applied on the top from this mass to the small mass to the up. There will be a tension force applied and down in here. At the same time, there will be a weight force down there too. We're going to talk about this at the end of the class, like in the middle of the class today. Okay, so this is where we're up to in the module 2, in the chapter 2. I covered, by explaining everything in here, I covered some of Newton's first law. Okay, so don't remember the Newton's first law as a law of the inertia. It's basically saying, hey, when something is in the stationary, it will not be in the stationary unless it get affected, like get pushed by some external forces. Just like, think about your pen on your table now, on your desk. Okay, it will be stationary unless you decide to pick it up. That's basically what the Newton's law stands for. Okay, and when you're like pushing it, unless it's getting some affected by other forces, it will kind of move stationary, moving the constant velocity as well too. All right, so let's move on some chapter exercise using some questions then. So page 42 of the workbook, please. So Newton's second law, as I said, kind of describing what the F equals ma, and I ask you to write it down. The true meaning of that is the net force equals to net ma last time too. Okay, this could be means that change mass times the acceleration. Okay, so net force means that sum of the masses times the sum of all the acceleration applied that to. So if you have a fixed mass, that mass will be just that fixed mass value, but you just need to find the acceleration of it. So what we're going to do, did we do question 1 last time? I think we did that. Okay. Do you remember what question? Bungee jump, we did that last week. Skier, did we do that? Question 3. Let's start from question 3. Okay, page 44, please. Question 3. Okay. A water skier of the mass 80 kilo, starting from the rest, pulled in a northerly direction by a horizontal rope with a constant tension of the 240 Newton. After 6 seconds, he has reached a speed of the 12 meters per second. Now, can you first draw a diagram about this situation here? Okay, and they show all the forces applied on the skier over here. Okay, you may see like there's tension force applied on the rope, so that is kind of dragging the skier to forward. Vertically, there will be a forces applied there too. There will be a weight force, and there will also be the normal reaction force R applied there, and there will also be some friction or the resistance force from that resistance, let's say R, from the water. So as you like kind of push, like you may expect like there's some water splash or like some resistance from the water. Okay, so these are the forces, all that forces applied, force factors applied on the skier over here. What we are given here is his mass is 80 kilo, but after 6 seconds, his final velocity is 12 meters per second, and initially, if you read the question really carefully, that starting from the rest, that's giving you that initially he was at 0. Okay, now from the given information here, that's time, final velocity, and initial velocity, we are able to find that how much acceleration the skier is now receiving now. Okay, how do we find that? We can use A is equals to B minus U on the T, if you remember the motion equation there. The 12 minus 0 divided by 6, giving you 2.0 meter per second squared, which means that he's now in the situation where receiving that 2 meters per second squared of the acceleration. Does it make sense? Okay, so he's getting accelerated. Remember what that means in here. Getting accelerated means he's having an experience and change in his velocity by 2 meters per second forward. So in another second, he will increase velocity by 2. So after 7 seconds, he will go like 14 meters per second, 8, 16, and 18, and so on too. Does it make sense to all you? Okay. So that's module 1, but revisit in the module 2 like this. All right. But the problem here is he's receiving the tension force of 240 newtons. We don't know what the net force is, and then what the question is asking you, A. Okay, so let's find the net force there. This is can we say this is a net acceleration he's receiving now, isn't it? He doesn't get any other acceleration. Does it go flying up, going upwards or downward here? I don't think so. He's intact in the water, just moving forward. So this is the net acceleration. Then simply for A, to find the net force, remember that you can use m times A or net m times net acceleration. What is the net mass of the person we include in the skier? Would it be 80 kilos? It's given. So it would be 80 times the net acceleration, which is 2, giving you that 160 newtons for the net force value moving forward. Okay, that's how we can find the net force value first of all. B, if the tension in the rope were the only horizontal force acting on the skier, what would be his acceleration? Then we are assuming that the net force is now not the 160, net force is 240 from the 40 newtons from the rope or the tension force. Then this is equals to ma, therefore net acceleration must be the net force divided by the m, that is 240 divided by 80, giving you that 3.0 meters per second squared in forward again. Make sure you put in the sig fix and the direction as well too. The question didn't ask you the magnitude, but just the acceleration. If you miss it out the direction here, you get you lose mark. And only 1 mark question, you get 0, even after this working out. Yeah, that's painful. C, what is the sum of the resistance forces on the skier then? Okay, now he's receiving that 160 newtons. So let's think about the net force, the true net force in the situation here, in this situation there. Okay, We're gonna ignore that, the vertical forces, because I know that he's not moving up nor the down, means all the weight and the resistance for the normal reaction force will cancel out each other. Okay, or you can simply say the net force on Y is equals to 0. Okay, then we can say that the net force is equals to the net force and horizontal forces that you only have applied, because we have the 0 vertical forces, which means we gotta add up all the forces that we have. What do we have? We have the tension force, which is moving forward, plus that negative the resistance force. So let's put that as FR. So why would I put the negative there? Because I know the FR, the resistance force, is moving backwards, okay, relative to this movement over here. So this gives you that FT minus FR. Therefore, the net force we found, 160, is equals to the tension force, 240, minus the resistance force there. Then the resistance force can be found from 240 minus 160. Okay, moving that. Then you'll get the 80 newtons for the amount there. Okay, are we done? No. Talk about the direction. Where will be the direction? What will be the direction of resistance force? It'll be 80 newtons backwards. This is it. This is how you apply the Newton's second law, or thinking about the motions. Okay, now could you try that question 4 then, please? There's an incline. Start with drawing the diagram first of the given situation, and then just analyze what the data, your information are given. Give me 1 more minute. So first thing, every single time you're dealing with the forces or like this type of the questions, always start drawing the diagram. It doesn't need to be a trolley, by the way. Just a box is enough too. At a time, sorry, I just drew that in a fancy trolley. Okay, and then what you need to show that clearly here is you need to show all that relevant forces applied in here. So and to read the question very carefully. We're giving that there is there's an incline, so there will always be the weight force, which is equals to mg, pushing it down. Okay, there will be no dragging force, by the way. The trolley is not pushed; it's gonna just comes down, so there's no pushing from the behind. So, but there is the normal reaction force from that. Okay, and assume that we have a given the friction. So, okay, you have to read the question very carefully at the end. The first part exerted constant friction force of the 270 newtons. Did you read that? If you didn't, you can't solve the question. You have to read the question very carefully. It means that there will be a friction force, which is always a constant 270 newtons down. Okay? So these will be all the forces applied. Remember that the trolley was not pushed. It was just rolling down eventually. There's no exerted force. Then what you can see from the weight force here is this has, so showing the weight force again, which is mg, has 2 components. So that would be mg of the x and mgy and mgx, other way around, mgy and mgx components in the right angle triangle over here with the angle of the 30 degrees in between. Okay, so let's make it in here. Mgy, which is the gravitational force of the y component from the right angle triangle here. You do know that this is be mg times cos 30. Mg of the x would be mg times sine 30. Okay, I just leave that like here too. Okay, everyone good up to this point? Then what we know about this situation? Okay, let's think about net force on the y-axis only, the vertical y-axis. That we have the normal reaction forces applied. Okay, now this wave force got divided into the 2 components, y and x. So in this situation here, you get the r, which is the normal reaction force, plus that 2, the mgy, but this will be minus mgy. Y is a minus because due to the direction is moving downwards there. So this gives you then r minus mg